All right, let's finish going over energy resources. And we're going to go to uranium now. Uranium is a radioactive element, and radioactive decay ends up producing heat. And so how a nuclear power plant works is inside that nuclear power plant, there's a reactor filled with uranium, and there's a controlled chain reaction. And basically, that means there's this constant amount of energy, heat energy, being released by this uranium. And, well, then works the same as that coal-fired power plant. This radioactive decay heats the water turns to steam, the steam turns a turbine, and the turbine turns a generator. But it's not uranium just that we pulled out of the ground that gets put into the reactor. In fact, this yellow that you see here is a uranium-bearing mineral. And then that needs to be refined and it needs to be concentrated into basically fuel rods, reactor-grade uranium, that goes into the nuclear reactor. And these are some of those fuel-grade uranium pellets that would end up going into the fuel rods of the reactor. And this is just a basic little diagram showing you that we have this reactor vessel. There's fuel rods in there, and then there are also control rods which control the nuclear reaction going on in there. And this gives off the heat that turns the water to steam and turns this turbine, which turns this generator, which makes the electricity that goes to your home. This is what a typical nuclear power plant looks like. It's going to have this cooling tower on it. And many people like nuclear power because it's viewed as being a kind of a clean energy source. Now, hang on, I'll get to looking at that in detail. But the reason some people consider this is in our nuclear power plant here, the only emissions that are going on are this, and that is steam. So that's just nothing but water coming out of there. And this water it's not radioactive. You could condense that, you could drink it, everything would be fine, no big deal. So like I said, some people consider it a clean energy source. I did put that in quotes because it's not exactly right. There are issues with nuclear power. Now, first of all, once you get a power plant going, it's not terribly, it's expensive to build one, but to actually generate the electricity, it's not too bad. Like I said, the only emissions you have from the power plant is water vapor, but some of the issues are things like locating your nuclear power plant. You really don't want to put your nuclear reactor on a fault line, because what if you have an earthquake? Like what happened in Japan, and then you could have some serious consequences from that. You could also have a meltdown. A meltdown is where that controlled chain reaction, that controlled nuclear reaction becomes uncontrolled, and radioactive material gets emitted into the environment. And this is what happened in Japan in 2011 following the earthquake. And this is what happened at Chernobyl in 1986 due to various human errors there. However, meltdowns are relatively rare. So, we've been using nuclear power for quite some time, and there's many, many nuclear power plants all over the world, but there aren't that many meltdowns. However, even though they have a good safety record, when something goes wrong, it is something really, really major. So there is that, you have to weigh the costs versus the benefits of this, just like with any energy resource. The last thing that can be an issue with nuclear power plants is radioactive waste. Eventually, those fuel rods are not going to pack enough energy to make more electricity, but they're still very dangerous. You can't just toss them out somewhere because they're still very radioactive. And so you have to think about, well, what would be a safe way of disposing of these? And right now in the United States, there's no repository for reactor grade nuclear waste from these power plants, so the power plants themselves store the waste on site. All right, so that's our uranium. Let's finish off energy resources looking at oil and natural gas, those hydrocarbons that I was talking about, right? Chains of carbon atoms bonded together with little hydrogens bonded to those. And oil and natural gas is the remains of marine microorganisms that did not completely decompose. So marine means this is being formed in the water. This is being formed in the oceans. And so you have all these like little plankton and other microorganisms floating around in the world's oceans, and when they die, they sink to the bottom of the ocean, and if they don't completely decompose, and if the conditions are just right, you can end up having oil and natural gas being created. Oil and natural gas gets refined into making fuel like gasoline and diesel. It's also used in making many other things like plastics. So any of the plastics you see around your house or that you might be using also are derived from these hydrocarbons. We do also generate electricity. It's become a lot more common recently to have natural gas power plants. Natural gas burns cleaner than coal does, but otherwise the power plant works the same way. It's just natural gas is being burned to heat the water, to make the steam and do all the other stuff. But it does have less emissions than a coal-fired power plant. So to have a hydrocarbon deposit, these things do not form everywhere. You need 4 basic things to make a hydrocarbon deposit. You need an organic rich source rock, right? You need something that has the remains of those little microorganisms. And oftentimes this is an organic rich shale, but it can be other types of rocks as well. It just has to be organic rich. And then this source rock must pass through the oil window. What the oil window is, it's the temperature and pressure conditions that are needed to break down the complex organic molecules into our hydrocarbons. And it's a window because it's very specific temperature and pressure conditions. Gets too hot, you burn the oil away. Doesn't get hot enough, you never create oil. And so it's those perfect conditions for creating oil and natural gas. Now, once this oil and natural gas is created, it can migrate, it can move around. And so it will move through pathways underground, and eventually it'll reach something we call a reservoir rock. And this reservoir rock holds the oil until we want to get to it. It has good porosity. Porosity is open space. And so it has a lot of open space that the oil can sit in, and it has good permeability. Permeability means if we drill a well into it, the oil easily flows from the rock into our well. And the last thing we want is a trap, because we need to keep that oil underground until we want to get to it. Because unfortunately, if the oil comes all the way to the surface, what happens? Oil is a mix of all kinds of different hydrocarbon chains. Lots of the shorter chains escape into the atmosphere. They volatilize. And those are some very useful parts of the oil. And all we'd end up being left with is kind of this tar-like sludge, which is not as useful. So we want that oil to stay underground until we are ready to use it. So we need a trap to hold that oil underground, and that trap has to be impermeable, meaning the oil cannot pass through it. So it's kind of like a dam holding the oil back. And like I said, if we don't have a trap, the oil comes to the surface and it can flow over the surface, but this stuff will congeal, we'll lose the good stuff, and we'll just get this nasty little like tar sitting there. Now, there are different types of traps that exist, and I'm just going to go over 2 fairly common traps. One is an anticline and another is a fault. So let me show you guys how an anticline works as an oil reservoir. So remember from structures, here's Earth's surface, and an anticline is an upward arched fold. So let's say we have a rock with good porosity and good permeability. So that could be our reservoir rock. And then above it, we have a rock like shale. Shale tends to be impermeable. So if oil gets into this rock from the source rock somewhere below, the oil will flow upwards and get stuck here underneath that impermeable shale, the trap right there. And the reason oil flows upwards, it's low density, so it wants to make it to the surface. So it's going to flow as far upwards as it can, and then it's going to get trapped behind that impermeable shale. And that's why anticlines make good traps. Synclines would not, because the oil would simply keep flowing away. You don't have that upward arch to capture it. Now let's also take a look at how a fault can trap oil. Faults are another classic trap. And so again, we can have Earth's surface here. Let's draw a fault in there. And let's say we have a nice porous and permeable rock. That's going to be our reservoir rock. And then surrounding this porous and permeable rock, again, we have impermeable rock. So if down here we have our source rock, it goes through the oil window, the oil will flow upwards until it hits this fault, which is impermeable, and the oil will accumulate behind that fault. We don't get any oil accumulating here because even if it was in this rock, it's going to flow to the surface and it's not trapped underground. So those are two classic ways that oil can get trapped underground, in these anticlines and these faults. Now, the oil industry in North America has a history that goes back into the mid-1800s. And in fact, the first commercial oil well in North America was here in Oil Springs. That's in Ontario. The Canadians beat the Americans by a year. The first commercial oil well in the United States was in Pennsylvania. Now, that does not say the first commercial oil well in the world. The first one in the world was, I think, in Azerbaijan, which is one of the former Soviet republics. But in any case, in Oil Springs, Ontario, was the first commercial oil well in North America. And the way they would extract oil, they'd build a structure like this, a drilling rig, and there would be a drill in there that rotates around and bites into the ground and drills a well, and once they hit oil, they'd put something like this on there. A steam engine would operate this and would rock back and forth. Each time it would go up, it would pull oil out of the ground. Well, what do we do today? Well, we do have some better technology today, but the basics are still the same. We have a rig. In there, there's a drill bit that rotates around and drills into the ground down to where we find our oil. And like I said, we do have some better technology than 1850s Ontario. Nowadays you can do directional drilling, you can drill offshore, but the basic thing of drilling into the ground to the place where the oil is, to the reservoir rock, remains the same. Once we reach that reservoir rock, we put one of these on. And this rocks back and forth, and each time it goes up, it pulls oil out of the ground. And so nowadays it's not operated by a steam engine anymore, but again, the basic principle is the same. And that's how we get oil out of the ground. So just remember, for the test, You need 4 things to create an oil deposit. You need your organic rich source rock. It has to go through the oil window. You need a reservoir to hold it, and you need a trap to keep it from coming to the surface. And let's see. Oh, hey, the random picture of the day. I put on dresses every now and then if it's something worthwhile, and my wedding day was worthwhile. It's kind of interesting. I'm standing a step above my husband, and he's still taller than me. He does look sort of like a muscular Freddie Mercury. He's giving me a look right now. Okay, to make it up, I will let you know, I will never ever say anything as inane as that was the best day of my life, because that would be really sad to me if your wedding, you can say that on your wedding day, but if you say that after your wedding day, that's like kind of sad, because if that's the best day of your life, you're doing something wrong in your marriage. You know, it should be like what I have with Paul. Every day with him is better than the last. Okay, he's giving me a look like he doesn't actually believe me, but it is true. So, cut. I said cheesy romantic things.